meet. I'm really happy to be closing this awesome meeting. I'm seeing a lot of faces down, which must mean the CO2 in this room is getting pretty high, but let's just try to get through 15 more minutes and we can all go eat. But today I'd like to discuss how we could potentially test the concept of the habitable zone. So in the near future, new and powerful instruments will allow us to characterize exoplanets like never before. So what you're looking at here are a few instruments that are or have been at least partially involved in detecting and characterizing exoplanets. Now, so far, we have not yet been able to directly observe Earth-sized habitable terrestrial planets. However, as we look to the future, we can look forward to instruments dedicated to observing these kinds of exoplanets, which we think may host life. So in particular, I'll be focusing on HabEx and LUVOIR right here, which are both direct imaging instruments that are in the running to become NASA's next flagship mission. And so they would directly image Earth-sized terrestrial exoplanets in the habitable zones of stars like the Sun, so G stars. And because for the first time in history, we'll actually finally be able to observe these Earth-sized habitable exoplanets, we may also be able to test some habitability hypotheses. So to do that, we could use a statistical comparative planetology approach, which essentially just means that we'd be taking quick and cheap measurements on a large sample of exoplanets to test a particular hypothesis. So in doing that, we really want to take the number and the diversity of exoplanets as an advantage. And a kind of real-life example of this is as on this cartoon here, where we'd essentially just be taking quick and somewhat imprecise CO2 measurements on, say, 50 exoplanets in the habitable zones of their stars. Now, a somewhat recent example of this approach is by Leslie Rogers, IU Chicago. And so this is for exoplanets. And Leslie took very low precision measurements of mass radius measurements for a large sample of planets to infer the radius at which planets are likely to become rocky. So this is a really great example of this kind of approach, because if we look at any individual point here, the error bars are huge. They're almost the entire size of the plot. So it'd be really difficult to infer anything significant from any one or two of these points. But by putting all of this low precision data together, Leslie was actually able to get a posterior probability distribution on the thresholds at which planets are likely to become rocky. So she found here that occurs at about 1.5 Earth radius. Now, what I'd like to do with this kind of statistical approach is to test the concept of the habitable zone. So we've heard it quite a lot this week. The habitable zone, of course, is defined as the possibility of surface liquid water between two orbital separations. And whenever a new planet or a new system of exoplanets is discovered, the discovery usually comes with whether or not they orbit within the habitable zone. However, in habitable zone theory, there's a lot of predictions and assumptions that we just have not yet tested observationally. Now, here's a slightly more scientific illustration of the habitable zone. So its distance and width varies as a function of stellar type. And usually the inner edge is taken to be this yellow curve here, which is the limit at which planets are likely to go into a moist greenhouse state. So they're going to start losing their water to space. Now, within this bluish region right here, we make an important assumption. So this is the habitable zone. We assume that the silicate-weathering feedback functions to regulate the climate of these planets. So the entire concept of the habitable zone relies on this climate feedback. So what is the silicate-weathering feedback? Well, it's a negative climate feedback that relies on the cycling of CO2 in and out of a planet to regulate its surface temperature. So an easy way to think of it is that if we have a terrestrial exoplanet orbiting in the habitable zone, but slightly further away from its star, so closer to the outer edge, technically its surface temperature could drop to below freezing. Now, luckily, when surface temperature decreases, the weathering rate, so the intake of CO2 by the planet right here, also starts to slow down. And because the outgassing rate is usually constant, CO2 is going to be able to build in the atmosphere of the planet and bring the surface temperature back to habitable conditions. So we have pretty good geological evidence that this feedback has been functioning on Earth throughout its history, but we have no idea whether or not it works on exoplanets. We just assume it does because it does on Earth. Okay, so let's just come back to this plot right here. What would happen if the silicate weathering feedback did not, in fact, function? Well, the outer edge would be found much more close in. So the habitable zone would be super tiny. So it's clearly super important when we talk about the habitability of any given planet and whether or not it's actually in the habitable zone. But in addition to bringing the outer edge much more further out, it also regulates the surface temperature of planets within the habitable zone. So instead of having their surface temperature go from 270 here to 373 Kelvin here, it's going to regulate the surface temperature to be more closely to that of the Earth, so around 290 Kelvin, plus or minus a pretty narrow uncertainty range. Now, the outer edge right here is usually defined by the point at which CO2 is going to condense out of the atmosphere of the planet. So therefore, the silicate weathering feedback can no longer function, and the planets found here are likely to be in a globally glaciated state, so in a snowball state. Okay, so we want to test whether or not the silicate weathering feedback actually functions on terrestrial planets. And if it does, and we observe a number of them and take CO2 measurements on each of them at different orbital separations from their stars, what we should see is that there should be a drop of CO2 with increasing irradiation. So to illustrate why that is, let's take this point right here. It's a planet orbiting further away from its stars with a lower value of irradiation. And because of that, if the feedback functions, it should have a higher amount of CO2 to maintain habitability. In comparison, this point right here is much closer to its star, and because of that, it should require less CO2 to maintain similar surface conditions. So if the feedback functions, we're going to get a downward slope right here. Now, of course, there's going to be a lot of uncertainties with this, with what exact amount of CO2 we can expect as a function of irradiation. So for example, the exact surface temperature, the surface pressure, other greenhouse gases, clouds, and of course, instrumental uncertainties. All of these are going to make it more difficult for us to see this downward slope. But the idea here is that the more planets we observe, the easier it will be to marginalize over these uncertainties, and so to be able to detect a downward slope despite our big error bars. Now, of course, well, probably if we observe thousands of exoplanets, we may detect a downward slope if the feedback functions, but even a crazy expensive futuristic instrument such as LUVOIR won't be able to see that many planets. So we want to know whether or not this test is at all feasible. So the big question I'm asking in my work right now is how many planets would we have to observe to detect a downward slope if the feedback functions? So to answer that question, first I had to understand how this downward slope changes as we vary our parameters. So here I'm just going to show you some examples of the kind of data I get. So this is using CLIMA, a radiative convective model, and SMART, a radiative transfer model. And this is the same axis as you just saw, CO2 versus irradiation, and everything else is held fixed except surface temperature. So if we pick a value of irradiation, say here, and we go from green to black, so from lower to higher surface temperatures, we see that we gradually need more and more CO2 to maintain these higher surface temperatures, which makes sense if the feedback functions. But what I wanted you to realize from this plot right here is that surface temperature is going to be a pretty important uncertainty parameter, as when we vary it, always within habitable bounds here, we see that the shape of the curves changes quite a bit. So this will make it more difficult for us to resolve over these error bars. It adds a lot of uncertainty. Now, in comparison, here's a similar example, this time for different amounts of methane. And we see that this time, when we go from green, so no methane, to blue, so current Earth levels of methane, and then to red, so our key and Earth levels of methane, we see that the shape of the curve this time doesn't change quite that much. So this is just to illustrate that some parameters, even though they're uncertainties, they may not matter quite that much. And other things such as surface pressure and temperature are going to really matter in this. Okay, so these were just some examples of the kind of data we're going to be using. Now, I'd like to lead you through a simplified explanation of the statistical method I used to answer the question of how many planets we need to observe to detect a downward slope and so prove whether or not the feedback functions. But first, we had to make some kind of assumptions on our uncertainty parameters. We don't yet know that much about terrestrial exoplanets, but we had to decide on how much we're going to, for example, let surface pressure, surface temperature, cloud opacities, and so forth vary. So here's an example for surface temperature. Here, so it's a normal distribution centered around the value of the Earth, plus or minus a pretty limited range. The reason we're using this in a bit of an optimistic manner here is because previous work has shown that if a planet has a functioning silicate weathering feedback, and it's in the habitable zone, it should really maintain its surface temperature around that of the Earth, plus or minus about 20 Kelvin. Now, if you're worried, if this is raising a red flag in your head already, it's okay. This is our really optimistic case. For each parameter, we've also considered a much more pessimistic case where, for example, for surface temperature, we considered a uniform distribution from 270 to 373 Kelvin. But anyway, for now, let's take it as it is and go through the statistical method. So first, we choose a number of model planets, say 3. So we're creating planets that may or may not exist. Then for each of them, we're going to draw surface temperature values here from the distribution I just showed you. So this is where these distributions are going to come into play. They help us create our imaginary planet. So if we were considering all of the parameters that in real life we'd be drawing values for them right here. So we draw a surface pressure value from its distribution and so forth. Then for each of them, we, of course, also draw irradiation values from a uniform distribution because the planet can be anywhere in the habitable zone. And then, based on these values that we've drawn, we're going to compute the corresponding amounts of CO2. So this is where our data that I showed you earlier comes into play. It's essentially a big multi-dimensional matrix of CO2 as a function of a bunch of other uncertainty parameters. Okay, so now we have CO2 for all of our planets. Then we're going to add some instrumental noise to these values because we're pretending we're really only measuring CO2 for these planets. And then we're going to compute the irradiation versus CO2 slope for these 3 points. So here I've illustrated the slope as being negative, which it should be if the feedback functions. But of course, because of our uncertainties in here, surface temperature, and in instrumental noise, in some of these cases, the slope may end up being positive or very close to 0. So when we repeat this whole process 10 to the 5 times, we're going to have a number of slopes that are negative and a number positive. And of course, the more planets we model, the more slopes should be negative because we assume the feedback function. Okay, so this slide right here illustrates the point I just made. So this is the distribution of slopes as a function of the number of planets that we would be observing. And so we see that for a low number of planets here in magenta, a good fraction of the slopes end up being positive, or at least very close to 0. But the more planets we observe, the more slopes are negative. So this makes sense, right? The more planets we're going to observe, the easier it will be to detect a downward slope if the feedback functions. But we had to decide on what's a good enough number of model exoplanets. So to do that, we define the power as the fraction of slopes with a p-value less than 0.05. So this is just how many slopes are clearly negative enough. And here, to get a power of 0.8, we see that in this case, we need 11 model exoplanets. So what this means in real life is that if the silicate weathering feedback actually functions on exoplanets, and we observe 11 of them, then we'll have an 80% chance of actually detecting the feedback. So if we want a higher chance of detecting it if it exists, we'll just have to observe more planets. Now, you may remember that I mentioned doing this for both an optimistic and a pessimistic case. So this is for the optimistic case, 11 planets. And for the pessimistic case, we'd have to observe 51 exoplanets. Now, some caution, these are still early results in the sense that they're for a fixed amount of CO2 noise, 0.5 log units. I'm currently working with Kat Feng from Santa Cruz right here on actually adding simulated Habex and Nouveau noise to these CO2 values. So that will come later. Okay, but are these values reasonable? They already give us somewhat of an idea of what we can expect. To answer that, we looked at some work from Chris Stark, who estimated the candidate yield for ExoEarth using different future generation instruments. So if we look here at Habex, it's a pretty small mirror, and because of that, we'll likely only be able to detect about 10-ish exo-Earth. So that's not ideal to do any kind of statistical study in general, which makes sense because HabEx isn't really being thought of in that way. But in comparison, if we look at LUVOIR A here, or even LUVOIR B, we'd be able to observe up to about 55 exo-Earths. So that's really an ideal number to be able to do this kind of statistical study. So to test the habitable zone in general, and especially to test whether or not the silicate weathering feedback functions on exoplanets. Okay, I'm going to leave my conclusions right here. Thank you.
Questions for Jade? I see Robin.
Thanks. So Robin Wordsworth, Harvard. I was wondering, have you thought about if you had ancillary observations, something like albedo, that allowed you to rule out, like the parameter space that was caused, you have a lot of dependence on certain parameters. If you could make other observations, add priors to your analysis, would that help things?
Maybe, but I guess, I mean, if these observations were available, sure. I can't think of any right now on the spot, but I think the whole point is that we really want to, because we'd have to do this for a large number of planets, likely maybe 50, we really want to make sure that we do this with only really quick and simple measurements. So here in this case, it's really advantageous because it would allow us to really only test for CO2, to have an estimate of the amount of CO2, and of course the distance to the star. But if we want to add other parameters, that may take longer, although if they're available from like test studies and such, yeah, that'd be great. Yeah.
Daniel here in the front.
How much LUVOIR time is this going to take overall? Like, I don't know. I assume somebody has done some reference studies, like to even detect like a crappy measurement of CO2. Do you need like order of an hour or order of weeks? Right.
I'm not sure yet. I think we're going to take that into consideration when actually computing the amount of CO2 noise. We're going to decide on an integration time, but we're not sure quite yet. Yeah, probably a few hours, weeks, I don't know. I'm not an observationer, so there's a lot of people in this room who'd be able to say that much better than I would.
Sukrit?
Yeah.
Hi, Sukrit Ranjan, MIT. Thank you for a really great talk. Just regarding the uncertainties, how hard is it to differentiate CO2 concentrations at very high CO2 concentrations?
How hard is it to differentiate CO2 concentration?
Yeah, I guess I'm wondering, is there any risk of saturation of the CO2 line, so it's hard to tell if there's too much CO2, or can you always get it from the wings?
Right, yeah, so like, I'm not going to go back, but as you saw on the plot, if we're at lower values of irradiation, the CO2 kind of on the plot, it starts being really straight. So we definitely want to be able to sample enough of this plot that we're able to see a downward slope, because if we only looked at planets at which there's a lot of CO2, we may not be able to get a slope at all, because I don't know if you remember, the plot kind of goes like this, right? That's a good point.
Hannah?
Hannah Wakefield, Space Telescope. How evenly distributed across the phase space of stellar irradiance do you need these 50 planets to be? And do we expect to be able to have such a distribution?
That's a really good question. All I can say is, again, the same thing. You definitely want to be able to sample enough of the plot that you have, the spot at which the downward slope is more obvious than rather at lower values of irradiation. But yeah, I'm not sure exactly. That's a good point, though.
All right, let's thank Jade again. And thank all the speakers of our session.